Okay, so in this problem, water is being poured into a tank which is a cone shape. Okay, so wait, let me kind of redraw. What? Okay. So let's say water is being filled into a tank which is a cone shape. So the radius here is, let me see, the radius at the top of the tank is 5 feet. The height of the tank is 15 feet. Water is being poured into this tank at the rate of 2 cubic feet per minute. So I pour water into this tank. Each minute I basically put in 2 cubic feet. The height of the tank is 15, the radius at the top is 5 feet. How fast is the depth of the water increasing when the depth of the water is 6 feet? Now you can kind of imagine if I pour water into this cone-shaped tank and I pour the same amount of water over time, you can kind of see at the beginning the water would have filled up pretty quickly. But at the end, because the surface is getting bigger, if I pour in the same amount of water in, you would see that it would not increase as much. So it's kind of the same thing when you actually drive. When you fill the gas, when you fill the gas tank, when you drive for the first maybe 10 minutes or half an hour, the meter would not move. But when you drive a little bit, the meter would have moved a lot quicker. So that's kind of the same thing here. If you drain water from the tank, drain the same amount of water, it would seem to drop slowly at first, but it will accelerate toward the end. So that's kind of how the I think that's how the gas meter in the car is engineered. You would see that you can drive a lot at first, but it would go out pretty quickly as you drive on. So if you look from the side of the tank, you will actually see this thing. So the side, the tank is a cone, but if you see from the side, it will look like a triangle. So this is 5 and this is 15. And I need to know how fast the depth of the water is changing when the depth of the water is 6 feet. So that means if I fill in water for a while until it's 6 feet in depth, so this is the picture that I'm looking at. I have a cylindrical, well not cylindrical, I have a cone, a circular cone. And I fill in water at a constant speed of 2 cubic feet per second. The radius of the cone at the top is 5, the height is 15. If I keep filling in until the depth of the water is 6, I need to know how fast this guy is changing with respect to time, obviously. So I need some parameter to work with. So let me do this. So let me say I'm gonna need to make a few parameters. The first thing that I need is the depth of the water. So I'm gonna call that the h. So h is my depth of the water, and let me actually also call r the radius of the water when over time. So if I want to find how fast the depth of the water is increasing, So it just seems that the question is basically asking for dH by dt. So this means the question is asking for dH by dt when the depth of the water is 6 feet. So that means when h equal to 6. So I have interpreted the question into a mathematical variable. I need to find dH by dt when h is equal to 6. What else do I know? I knew that yeah. I knew that the water is being filled into the tank at the rate of 2 feet per minute. So what does that really mean? That means the volume of the water in the tank is changing. So this 2 cubic feet per minute, this is actually the rate of change of the volume. So the question is actually giving me the V by dt. So that means the rate of change of the volume over time is going to be 2, because that just means I pour in 2 cubic feet of water into the tank each minute. So it seems like I have volume, I have radius, I have height, so it kind of makes sense to put it all together. So let me kind of put it this way. So what is my volume anyway? The formula for the volume of the water, that's going to be just 1/3 pi r square h. So this is once again the typical volume formula. Now this is quite special because the r and the h, they are not independent, because if you actually look at this diagram again, I hope you can see, but they are actually similar triangles. So geometrically speaking, the ratio of the size of the two small triangle and the big triangle here has to be equal. In other words, the r, let me see, the r over h actually has to be equal to 5/15. So the ratio of the size of the smaller one, the r by the h, has to be equal to the 5 by the 15. So that just means r has to equal Okay, so let me finish this by, I'm not sure how long this is gonna give me. Okay, so let me finish it by 10 minutes, hopefully. So r is gonna be h over 3. Okay, I don't know what wasted memory here, I mean my battery here. So let me go a little fast, I guess. So because r is h over 3, so I can simplify this guy to 1/3 pi h over 3 squared times h. So that's gonna be pi over 27 times h cubed. Now, I have dv by dt and I want to find dh by dt. So I can take the derivative of this thing. I'm gonna get dv by dt. That's gonna be pi over 27 times 3h squared dh by dt. I knew dv by dt is 2 and I know h is 6. So I can plug the whole thing in. I'm gonna get 2 equal pi over 27 times 3 times 6 squared times dh by dt. So I can solve this whole thing and get dh by dt to be just 1 over 2 pi feet per minute. Aha, so I can finish this in and still have battery left. Okay, good. So lucky for us, this is actually the last example that we have. I put the a little something here just for you to see. So a lot of what you see in the future are actually gonna have to do with derivative of something. It's actually gonna have to do with partial derivative. So the stochastic differential equation in those lemma and the Black-Scholes equation. This is gonna be what you will see, I think, in third year or fourth year. But you can see the formula pretty much involves the partial derivative of some term with respect to some term.
Remember the formula?
Probably not for this course. And by the way, I'm probably not gonna put the question that has to do with geometric stuff on the final as well, because I think in actuary you will not have to do much with. I think this is engineer stuff, the cone thing and the cylinder things. So I'm probably gonna put more stuff about the financial application. So that's actually all I have to say for today. Let me actually turn this off. I need to save my